Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today's question comes from Rick, W0EWN, okay? And he says, if you disconnect the circuit at the exciter and resistor, leaving the inductor and capacitor, will the circuit ring forever? This is a question about tank circuits. Okay, a tank circuit, you'll recall, is composed of a capacitor and a coil. Okay, and there is a frequency that is the natural frequency of this equals, let's see if I can do it from memory. 2 pi LC, 2 pi square root of LC over 1. Okay, so here's your C, here's your L. This will ring, let's call it ringing. If you put a spike, for example, there's a key here and there's a battery here, and this comes up to here, and you touch that to that and spike this, this thing will ring at its natural frequency. What happens is this charges the capacitor, and then when you open this, the capacitor will discharge through the inductor, which creates a magnetic field here. The magnetic field collapses and creates more current, which moves this to the opposite charge in the capacitor. Then it reverses and does that. This circuit right here is called a tank circuit because it contains energy. Okay, then there's the natural frequency. Now, what the output of this actually looks like is something like this. You get it's got a damped wave, and this is an exponential curve right here, exponential decrease, okay, in the curve. Okay, now why does it damp? Why does it damp? The actual tank circuit, if this is a pure capacitance and this is pure inductance, LC, if this were pure inductance, pure capacitance, this thing would ring forever. But where's the hitch? There's no such thing as a perpetual motion machine. So as the current goes through here, the wire has resistance. Okay, that resistance will actually dissipate energy as heat, and that's why you get the ringing coming down. And you can actually run the formulas and calculate everything that will happen. By the way, there is a quality factor for this circuit. Okay, this is non-dimensioned, and it is, the quality factor is high when the resistance is low. The quality factor is low when the resistance is high. So if you have a circuit that rings, say here, at 1 kilohertz, okay, and this is the amplitude of that, you will see this start there and then go down. Now, if this thing has a high quality factor, you get the thing ringing like this. You can get some components of the ringing out in here. It will ring at 1 frequency, but if you were to use this as a choke, that would allow just those frequencies through. A low Q circuit will have a much broader frequency response and not as high. So the measure of the height of the bad to the good is Q. And so when you see high Q circuits, it means they're very narrow band and they respond well to just a few frequencies. A low Q circuit, like the amplifier in your transistor rig, actually is round here covers the whole HF band. And they don't use the Q factor. They don't use the Q factor as part of their amplification scheme. Transistor amplifiers don't need tuning because they will broadcast anything. They are, quote, broadband. The old tube circuits had to use the resonance of tuned circuits in order to work. That's how they got their power up where it needed to be. And so there are a lot of tuned circuits in there. And every so often, every 20, 30 years, you may have to realign a super heterodyne receiver. The key thing about the superhet is that the way it's set up, all those circuits in there that need to resonate at specific frequencies all change at once. There's gearing or ganging or something in there that allows them to all move at once. And getting them to all move at once is called alignment. You don't have to do that with transistor circuits because they are inherently broadband. Okay, so we don't have to worry about Q all that much for that. Now, where it becomes important in antennas, a somewhat lower Q antenna would cover, say, the entire band at less than 2 to 1. Okay, that'd be a fine antenna. If it covers the entire band at less than 2 to 1, so much the better. And the same things that affect Q in the tank circuits, like resistance and so on, go to work in antennas too. So if you have very thin wire because you've got to hide it, you may end up with a higher Q antenna that may not resonate all the way across the band. If you use thicker wire, you will have a lower Q because there's less resistance in the circuit. Now, some antennas are inherently extremely high Q, and one that is that way is the magnetic loop antenna, which will only be resonant over a band of about 10 to 20 kilohertz, just part of the band. So you can't use it as a broadband antenna for your spectrum scope. It just has that one little section right there. But when it is there, it's every bit as good as a dipole when you have the thing tuned up properly. So I hope that helps answer some questions. There's no such thing as a perpetual motion machine. There's always some resistance in the circuit. If nowhere else, it's in the leads. And the coil itself, after all, is made of wire. Wire has a certain amount of resistance per foot. And so that will warm it a little bit and warm the other wires. The capacitor will not generate heat, should not generate heat, but there's still wiring inside. And the plates of the capacitor are metal. And if you put too much current through that capacitor, it will melt and pop. Same with an inductor. You can melt it, pop it. Create havoc with your machine. The problem with breaking one of those things is that it may very well destroy the object that that circuit is in. So be careful. No perpetual motions machines. There's no such thing as a free lunch. So there you have it. If you'd like to help support this channel, go to dcasler.com/support. If you like, you can subscribe and click the bell. You can click like, you can share this video. Lots of good things that you can do that help YouTube think that we're a great group of people. And until we next meet, 73.